Welcome in. All right, so the quotient rule for derivatives, and I want to do it by example. Now, the quotient rule itself is not super hard to try to memorize. You can certainly find some kind of a mnemonic for it. And what it is given right here. So if you have a function, now it's quotient rule because of the fact that you are talking about a numerator that is some kind of a function of x, and then a denominator that is some kind of a function of x. So for example, you might have something like this. So this would have been your numerator, and notice that it has an x in it. And then this would be your denominator, and it also has an x. So when we have this quotient in here, how do we take the derivative? So it turns out that the derivative itself can be actually taken, and here is the result. Now, it's not a very pretty result, because if you look at it, there's a couple of things to remember, or maybe more than a couple, but there is some kind of a pattern. So for those who remember the product rule, if you look in the numerator, it very much looks like the product rule, except that there is a difference or a subtraction right there in the middle. And then the only thing that's really different is that now you have a denominator, and that denominator is actually the original denominator, but it is squared. So that's how I kind of remember it. So I think of it as the product rule, and I'll put up the product rule up above there, okay, if you have forgotten it. And you think of it as a product rule with the subtraction, and then the denominator is squared. So how would you apply it, right? So that's the idea of this particular video. Now, if there is someone in here who wants to know how this product rule comes about, if you want to kind of prove this, that this indeed is the derivative, then I would encourage you to watch the proof, which I did, and I'll put up the link up above there. Now, before I continue, I do want to mention that we are making a very key assumption, that both the numerator is differentiable, and then the denominator is also differentiable. Okay, so those are the two assumptions that we make. Now, in this video, what I'm going to do is I'm just going to show you the derivative itself, so the actual application of this on several examples. Okay, so the examples will be a little bit easier, which is like this one. And then I have several examples which slowly are going to get a little bit trickier, especially the ones that you see there, function number 2 and then function number 3, which is going to be a little bit of work for us. So if I come back to this and I think about this quotient rule, then what it says is the following. So I'm supposed to take, so notice, the derivative of the numerator. So that's this right here. So if I want to take the actual derivative or obtain it, then I have to take the derivative of the numerator, so that's going to be just -2. I'm supposed to be multiplying it by the denominator, so the denominator is 3x squared minus 5, so I don't do anything to it. Then I take a subtraction, and I continue. Now I write out my numerator, so my numerator is -2x. I'm going to put that inside of the bracket. And then I'm supposed to take the derivative of the denominator. And then the denominator, or the derivative of that, would have been 6x. So that's what we would have right there. And the entire thing, so if I go all the way through, I'm supposed to now take the whole denominator, which is 3x squared minus 5, and I'm going to square it. So this complicated function that you see here, which we call the derivative, is actually the result of this quotient rule. So I just applied it over here to this function. Now, you can massage this, you can do whatever it is that you like. As a teacher, I probably tell most of the time students, if I'm just asking them for the derivative, just leave it as this is, so that you don't start, plugging away unless you're using the derivative for something else. Now, sometimes teachers will ask you, to actually provide you the domain for the derivative, and that's then a little bit different. So if you had to provide the domain, then indeed you have to do a little bit of work. So for instance, in here, in terms of the domain for this derivative, I would have to worry that my denominator right here is not equal to 0. So if I wanted to find the entire denominator in here, okay, and try to see what that denominator is, so I would say, all right, if I want to find what the domain is, then I have to put a restriction that the 3x squared minus 5 squared does not equal to 0, right? Now, that's the actual restriction. So if you wanted to solve this throughout, this actual square doesn't matter as much, but we are interested in to see, okay, 3x squared minus 5, when does it equal to 0? So now solving this whole thing, I would get 3x squared is equal to, I can bring this over to the other side, so that's going to be 5. I'll divide by 3, so what I'm going to get is x squared is equal to 5 over 3. Then I'll take this square root, so this is x is equal to the square root of 5 over 3 as so. So this is really what I would have, and this could have been positive or negative. And x cannot be equal to that because in those two instances, then what I would have is I would have this to be equal to 0. And that's not what we have, or at least that's not what we want. So that means that the derivative is actually not differentiable in those two cases. So this is the derivative, and here is the restriction. So the domain is x can be anything, but it cannot be plus or minus the square root of 5 over 3. Now, let us take a look. I want to just show you kind of quickly, because I'm going to pull up Desmos to try to graph this so that you can actually see, okay, this restriction come out into play. And then for the future examples, I'm not going to worry about these actual restrictions. I'll just be taking the derivative. So here it is. So here is Desmos. And let me pop in the actual function itself. So I have f right here. Fx is equal to negative 2x all over 3x squared minus 5. So this looks like a crazy function in here. Okay, so notice this is what we have. And even for this function, notice that it is not defined, okay, at those particular points. So if I substitute it in here, so if I wanted to know what the actual point is on this function, so let's say that I would have said f at, okay, let's say negative, and this was square root of 5 over 3. Okay, so notice that it's undefined, right? So the actual function itself is not defined there, and it's also not defined if I go back in here, okay, and if I put just a positive, it's also undefined. So the function's not defined there, it's defined everywhere else, and it so happens that the derivative is also not defined there. Now, pretty neat thing, because we can take the derivative, and the way to take the derivative, if you ever wanted to, you can actually do this. Okay? So if you do this in Desmos, as you are going through, if you put that little prime, Desmos knows that you're trying to look for the actual derivative. And notice that the derivative looks something crazy like this. And notice it is not defined at those instances. So the derivative of, so the square root, okay, this would have been 5 over 3. Let me just go back and erase that. Notice that it's undefined, and we can see that the derivatives are spiking there, right? So that's on the left-hand side at negative square root of 5 over 3, and on the right-hand side, you see the same thing. That's why you see those peaks there. Because the derivative is nothing else but a function. And it is telling us what the slope is at every single point. And it turns out that for us, okay, it's just not defined in those two instances. So that is something that you can look towards Desmos for if you ever wanted to see a visual. So now let's come back to this quotient rule and try to apply it to several examples, but I'm not going to put these restrictions not to make the video too long for you. I'm just going to be interested in applying this quotient rule right here to the examples themselves. So let's take a look and see what happens. So here's my first one. So that's my first example. I'm going to copy it. Let's bring it down over here. And I want to take the derivative of this. So this would have been take the derivative of all of this function with respect to x. So that is a notation, a different notation that we use. Well, this is equal to, so it is the derivative of the numerator right here. So that would have been now 18 times 3. So I guess that's 30. That's going to be 54. So 54x squared. So that is the derivative of the numerator. Now we're supposed to be multiplying by the denominator. So that's going to be just that. Minus. Now we're keeping our actual numerator constant. So we do nothing to it. And then we take the derivative of the denominator. Now the derivative of the denominator, I'm going to rewrite it here for us. So that's what it is right there, which would be nothing else. Now the derivative is 1/2 as we drop that in front. And this is going to be now negative 1/2. So that's what we would have in here. So that's over here, I would have 1/2 and then 2x, and this is negative 1/2. That is the derivative of that denominator. Now, of course, you have a half there, so you can take the half, bring it out here, so this can become a 9, okay? And then you can massage it as much as you like. So I'm going to leave that massaging for you because I just want you to understand the quotient rule with respect to this example. And now in the denominator, so what we would have is we would have this 2x, and this would have been squared. Now, because of the fact that I have the square root and the square, so the denominator really is going to become 2x. And this will depend, you have to talk to your teachers, how much do they want you to simplify these. Some of the teachers will just simply, apply the apply the quotient rule, and then take it and then leave it as it is, because the more that you start simplifying, the more prone that you might be to an error. Okay, so this is the result of that first example. Let's take another example, and these examples I didn't make easy on you at all. So when you're practicing these on your own, just be careful as you're stepping through this whole kind of junk that you have in here. So we're taking the derivative of this function with respect to x. And again, if we want to try to apply the actual quotient rule, then in this case, I have to take the derivative of the entire numerator. So that's not going to be too pretty for me. So this is going to be, so that first one, this is the same thing as writing it in this way. So the derivative of that is equal to 4. Notice that 1/2 will come up to the front. This is now x to the negative 1/2. That's the derivative of this. And then we have minus, so now the derivative of this is going to be 10x to the 4. So that's the first derivative of the numerator. Now I'm going to leave the denominator as is, so negative x plus 2x squared minus, now the numerator stays as it is, so this would be that minus 2x to the 5. And now we take the derivative of the denominator, so that one's a little bit easier. That would have been negative 1 plus 4x. And now all of this has to be divided by the entire denominator squared. That's what the quotient rule, or the application of the quotient rule, is. So if you look at this, it's super ugly, right? I've been mean to you. If you're taking this and you're working through these types of examples, these are rather on the harder side that you would have. you typically, when you apply the quotient rule, especially in the beginning of calculus and studying it, then you're going to have much easier examples, which maybe are something like this, or, something that you've seen over here. So those are the simpler types of examples. Let's do that last one. So for our last example right here, so that's this function number 3, which is this. So I'm going to copy it, and I'm going to bring it down for myself. So now I want to know what the derivative of this is. So take the derivative of that with respect to x. What does it equal? Well, let's try to find out. Another nasty one. So for this one, notice that within here, what I have is not only will I have a quotient rule, I'm going to have to use the chain rule. I'm going to have to use the actual summation rule. So I'm going to have quite a lot to do here. So this is a nice example of trying to bring in all the different rules together. So if I take this, then this is what I will get. I'm going to bring this in, and this, as a result, in terms of the quotient rule, is the following. So the derivative of the first piece is going to be, so I'm going to put it in brackets. So this is 3 goes in front. All right, so that's this 3. And now this is going to stay the same. That's what I have over here. This is going to be squared. But now, because this is the chain rule, I have to now take the derivative of what I have inside of there. So that's going to be 6x squared minus, now take the derivative of that, which is going to be 1/2 x to the negative 1/2. That is the derivative, unfortunately, of the numerator. And now all of this is going to get multiplied by 3x squared minus 1, which is the denominator. Now, next, minus. Now I'm going to leave the numerator alone. So 2x cubed minus. Okay, this is to the cube. And now I'm going to take the derivative of the denominator. So now taking the derivative of the denominator, that will be 1/2 of all of this, 3x squared minus 1 to the negative 1/2. And then this is being multiplied by the actual derivative of inside. So I'm using the chain rule in here as well. So this is going to be 6x. And that is my full derivative of this. Now, so because I've subtracted, notice how complicated and crazy this is. I still have to divide this by the denominator squared. Now, I do notice, so in this particular case, I have a square root. So if I square this, then this is just going to be 3x squared minus 1. That is crazy, right? So that's a complicated derivative that you would have. You can massage it all you want. I wouldn't recommend it. I typically would just kind of leave it as is, unless, again, your teachers want you to do something. But all I have done is nothing else but here is the derivative of my numerator multiplied by my denominator minus my numerator, which now stays the same, multiplied by my derivative of the denominator, divided by the denominator squared. That's what the chain rule actually does. Now, before I let you go, in all of these examples, as nice as the quotient rule is, I very often do not actually utilize the quotient rule because I will change my actual functions to simply be and take advantage of the product rule. Now, what I mean by that, I'm going to just illustrate it on this one example, and you can apply it to all the other ones. So if your teachers ask you to do a quotient rule and find the derivative by the quotient rule, then yes, you have to do this. But if they just say, find the derivative, and they don't tell you what to use, then in those instances, you don't have to use the quotient rule throughout. You can use anything that you like. So for instance, in this example, I can say, okay, this is the same thing as negative 2x multiplied by 3x squared minus 5 to the negative 1. And what I have here is just the product rule. So if I wanted to take the derivative of this, I can just say, well, I remember my product rule. My product rule says, take the derivative of this, negative 2, multiply by my second function, which is 3x squared minus 5 to the negative 1, plus leave my first function alone and take the derivative of this. So now the derivative, let me just shift this over, of that second one is indeed, so that would have been negative 1 times the 3x squared minus 5 times the actual derivative inside, which is 6x. And that is it. And now from here, it's actually much easier to try to massage this. This is just negative 2 all over 3x squared minus 5. And then within here, what I have is, so this is 2 and a 1 and a 6. So that's going to be 12. And notice the negative and the negative will cancel. So that's still plus. So that's going to be 12. And then my x and my x. So that is going to be x squared. And now I actually missed this here because I was taking the derivative. So this is negative 2. So this is now 12x squared all over, notice, 3x squared minus 5 squared. So it's much easier to massage it from here. And to be honest, most of the time I will use this product rule instead of the quotient rule, unless somebody tells me. Or I'm teaching it as I'm teaching it in this particular video through the examples. So even for those that I pointed out who wanted to see the proof of the quotient rule, I proved it using the product rule. So if you would have gone into that video, you would have seen that that's exactly what I used. And they are equivalent. All right. Now, I'm not going to do all the other examples by the product rule, so changing it back. But please remember that you can always rewrite the denominator and then just put an exponent of negative 1 because that's exactly what it is. All right. So thanks for watching. It's been a lot of fun. Okay, with respect to all of these different rules, I'll try to do a full summary and a lot of examples, maybe in a separate video. Thanks. Bye, everybody.